Hi everyone, I'm Sam Alcaine, Assistant Professor at Cornell University, here giving an update on our project, Fermenting Value for Dairy, where we're evaluating skim milk as a substrate for the biomanufacturing of value-added ingredients and products. Now, to give you a little bit of a refresher on this project, because I'm sure it's been a while, the impetus from this project arose from some of our earlier work on fermentation of dairy byproducts like yogurt whey, sweet whey permeate, and milk permeate by a yeast called Brettanomyces claussenii. Now, that yeast was fermenting lactose into ethanol. And what we found in some of that earlier research is that when we hydrolyzed the lactose before that fermentation, that Brettanomyces claussenii would utilize the glucose but leave behind the galactose. And this galactose had some potential because galactose is a low glycemic sugar. It is thought to maybe have some impact on mental function. It is twice as sweet as lactose, and it's also important for the creation of hepatic glycogen, and glycogen is kind of one of the powerhouses, the storage of power for the cells. So like if you're an athlete and you kind of run into the quote-unquote wall, it's because you've depleted your glycogen reserves. So being able to create galactose-rich products might be important. Now, we've done a lot of work on the dairy byproduct side, and the issue came up that sometimes there's excess skim milk and excess skim milk powder that we don't know what to do with. And so potentially the question was, could we utilize Brettanomyces claussenii to then create galactose-rich dairy streams from skim milk? And that's kind of what we have going on there. And then those galactose-rich streams could be beverages. They may have ethanol in them, but still have that improved alcohol. Or maybe they could produce novel products or serve then as substrates. That galactose could serve as substrates for other things like galactoligosaccharide production or the extrusion of novel products. But really, this part of the project focused specifically on the fermentation. So what were we looking to do? We had two primary goals. One, the overall evaluation of the fermentation of skim milk and milk concentrates by Brettanomyces and related yeast species to see what type of galactose-rich fermented milk we could produce, and then looking to see if we could do some optimization around the fermentation parameters for galactose production. So for that first objective, that initial evaluation of fermentations of skim milk by yeasts, right? We looked at 4 different yeasts: Brettanomyces claussenii, the one that we've traditionally been working with to successfully convert lactose into ethanol; Brettanomyces bruxellensis, which is a relative of the Brett claussenii that doesn't utilize lactose, utilizes glucose but not galactose; and then Cluveromyces marcianus and Saccharomyces cerevisiae. It's kind of our control yeast. And we did this in the small scale, benchtop scale there with 250 ml bottles. And we looked at fermenting with different lactases levels, with and without lactase. We fermented at 30 degrees C. And then we kind of wanted to see what was going on. You can see this is what the bottles look like after fermentation. You see that, right? They got a little chunky, but we'll get to that in a minute. So here are the results of some of the fermentations. What you see here is a graph of density. So as the yeast ferment the sugar into ethanol, the sugar is heavier than water. The ethanol is lighter than water, so the density of the liquid during that fermentation as the sugar is utilized drops, gets lighter. And that's a way to help us track the fermentation with yeast over time. And so what you can see here is fermentations where we had the lactase added and no lactase added. Not surprisingly, when there's no lactase added, just our Brett claussenii and our Cluveromyces marcianus, they do a good job of utilizing the lactose and producing ethanol, which you can kind of see over here in the table here on the bottom right. Now, when we add lactase, we see a nice diversity of sugar utilization. Here we see the Brett bruxellensis is just utilizing the glucose and very little galactose. And you can see here at the day final of the fermentation, this is day 0. Over here, day final, our galactose levels with the bread brucellensis are quite high, around 7 grams per liter. We also see here with our Brett Clausenii here in the green, it doesn't ferment all the way down as it does when it's fermenting just the lactose. And so we do see some residual galactose, which is what we want, nearly 4 grams per liter. It's a bit lower than what we've seen with our other dairy byproducts, and we don't know if this is an impact of pH, protein level, or what. But we do get residual galactose, not as high as we expect. We expected it to be closer to the brucellensis. And then, not surprisingly, there's very little galactose left by the Cluveromyces or the Saccharomyces. And you'll see here, right, the residual galactose not detected here and quite low with the Marxianus. We do get, again, as I noted, with or without lactase, some ethanol production, which also means there might be some options for alcoholic beverages out of this. Definitely residual galactose, but as you noted in the picture before, there's a bit of coagulation going on with these fermentations. With our dairy byproduct work, right, there was no protein there, so that wasn't an issue. So there's a question around, well, what do we do for future processing? So we started to ideate and think about what was possible. And you know me, I'm always looking for inspiration from other products around the world. And so we found some inspiration by this product called Calpis, which is a product out of a milk product out of Japan, inspired by a fermented milk from Mongolia. And this has skim milk powder in it, right? So it was like, all right, so we can still utilize skim milk, but what it does differently is that it actually acidifies the milk quite low, lower than what we do, right, with yogurt, right, to a pH below 3.45, and then it heats the proteins to make them, right, more stable and stay in solution in a way that they wouldn't if we had just dropped the pH during a normal fermentation. You saw that coagulation earlier. And then this way we could still use skim milk powder as the substrate for fermentation, hydrolyze it, and then potentially leave behind the galactose. And so here again, we fermented it with the same group of yeast that we like to work with here in the lab. And then you can see that the product looks much, much different, much better, right? Here you see this nice, milky, opaque beverage at the end of fermentation, and not that goopy coagulation that we saw with those other trials. And when we look at the fermentation results, then we also see some similar things. So here on the fermentation, again, these are those density graphs that we saw earlier with our yeast. The graphs with lactase and no lactase added. And so what you'll see here again is that the two Bretts, the Brett brucellensis and our Brett Clausenii, do not ferment all the way down to a low density, which means suggests they're leaving behind residual galactose. Whereas the Cluveromyces and the Saccharomyces ferment quite low. And when you look at the lactase treatment at the end of fermentation, you walk away with that same thing, right? We see residual galactose here, 7.7 grams per liter, and a little over 5 grams per liter here on average for the Brett Clausenii. Actually, we had one replicate that fermented quite a bit out of the galactose, but the other two left high levels. And a thing to note here is that the skim milk amount that we used was much lower than in those initial fermentations. So by percentage, a high level, nearly 50% of the galactose is left behind. And we let this Brett Clausenii ferment for a few extra days beyond the Brett brucellensis because we weren't quite sure if the fermentation was done. And if we had stopped it here at the same day, we probably would have had essentially the same levels of galactose between the two, which means we would have left essentially 50% of the sugar, 100% of the galactose behind. So we could make a galactose-rich product. And another great thing here is that the ethanol levels are quite low, nearly 0.5%. Which is what we want for a beverage that is going to be considered non-alcoholic. And so we could probably optimize that a little bit more to ensure then, right, that we had a beverage that would be classified as a non-alcoholic beverage, but still have high residual galactose, which might have then some functional benefits as a beverage. The other positive thing was that when we did our informal sensory on these beverages, that aromatically and taste-wise, they were actually quite pleasing, particularly the Brett Clasenii. And so, again, it suggests that there are options then for, looking at a little bit of flavoring, like a little strawberry. You can see like a light strawberry kind of milk product here, or something like that made out of this. And so there is definitely some potential here for some galactose-rich beverages using skim milk powder and selective fermentation to produce them. Then lastly, for our third objective, we were kind of looking to see if we could optimize some of that initial work with skim milk powder and its fermentation to leave behind higher levels of galactose. So we focused on just our Brett Clasenii, which is our best yeast, right, for leaving behind galactose and creating products that have positive aromas and flavors. And so we tried 2 levels of concentrated lactose, right, of adding skim milk powder to have high levels of lactose, so a 50 gram per liter lactose level and 100 gram per liter lactose level. And then we tried increasing levels of the amount of yeast that we use to do fermentation. And so the big takeaways here are that, yes, yeast concentration has a big impact on residual galactose levels. The lower the level that we pitch with, the more it'll ferment through the glucose and give us a chance to just stay with the galactose. Interestingly, at a high level of lactose, so 100 grams per liter lactose, our mid pitch level of around, this is around a little over 10 million cells per milliliter, it plateaued quite nicely here, stopped using the sugars, which might suggest that there's a high level of galactose left behind. We are still waiting for our HPLC results. There was some hang-ups at the lab with staffing because of COVID and getting through results, but those should be coming in shortly. It'll confirm our density graphs, and then we'll be ready to go forward with those results. And so what that means is that there is definitely a potential to use skim milk as a substrate, hydrolyze the lactose that's in it, and then selectively ferment out the glucose to leave galactose to create a novel set of either beverages, produce low alcoholic products with functional benefits, and maybe produce a new category of products. I will say here on the yogurt thing, from what I've seen with this yeast, the Brettanomyces clasenii, I don't think it's ideal for yogurt production, but we actually have come now across some lactic acid producing yeast that I think have some very interesting potentials in this space. We'll see where that goes on some side projects going forward. Another thing to highlight here again is that Lucas Wise, the student that has been diligently working on this project, presented some of that Objective 1 work last summer at the American Dairy Science Association annual conference, and he won second place in the animal nutrition poster competition, which I think is a huge credit to him and the data that he was sharing, because this was product development, not really animal nutrition, but he was so strong that he even placed second in that group. Again, Sam Alcaine, look forward to seeing you all in person for questions, and if you have anything else you want to reach out to me about, there's my contact information.